I'm going to talk to you mostly about continuous verification, which builds from a chapter in the chaos engineering book, but it's also something that we're seeing around the industry a lot more frequently now. I'm from a company called Verica. I'm not going to talk about that at all, really. So what is continuous verification? Well, so my company did a lot of research in 2019. And one of the patterns that we saw is an evolution from CI to CD to now CV. So if you think of continuous integration as not just your tools, but an advantage, a pattern where you limit the rate at which people generate bugs, because mashing code together basically creates awareness of the bugs. So it limits that rate because people writing code in isolation can write geometrically more bugs, right? So basically CI allows us to deliver, to build features faster as engineers. And then CD comes along and puts the code in front of customers faster, right? By automating that pipeline, we can now write the features faster and get them into production faster. So we can ship fast, but we want to ship fast and not break things. So CV, continuous verification, basically ensures that we continue to get the business properties that we want out of a system, while we're able to still generate features quickly and put them into the process quickly. So one analogy that I like when we've been talking to companies about this is CI is like building a faster engine, CD is like stepping on the gas pedal, and CV is like keeping your eyes on the road. So in our surveys of the industry, we find that most companies have a pretty good handle on CI. They have CI processes in place. Most companies that we speak to are in the process of, they're on their continuous delivery journey. They've got, at least some rudimentary stuff in place, and they might be, on an introductory level where they've got things wired together with Bash scripts and Jenkins, or they might be using more sophisticated tooling like Spinnaker or one of those. But they're somewhere along that journey. And a few are starting to dip their toes into continuous verification. And chaos engineering falls under the umbrella of continuous verification. So I'm going to talk specifically about continuous verification, but I'll also tie that into why this is necessary and how chaos engineering contributes to some of that. And I'm not a host, so if somebody who is host can mute people who aren't talking, that would be great. So a little bit more about the definition of continuous verification. It's a proactive experimentation tooling discipline for verifying system behavior. So I'm reading across the top of these axes here, comparing it to other existing disciplines that we're probably more familiar with in the industry. So this is not to say that the things along the bottom are bad, far from it, but we distinguish continuous verification from existing practices, which tend to be reactive testing methodologies that validate known properties. Happy to talk about any of these axes in particular in the QA, but just to give you an example, from the first one, if you think about most of the disciplines around availability or security also, but mostly around availability, almost all of them focus on time to detect and time to remediate, which means they're happening after the incident, which means they're by nature reactive. That doesn't mean they're bad things. Obviously, we need incident response management and alerting and all of that, the same as we need testing and all the other things at the bottom of the spectrum here. But continuous verification is a proactive discipline. So there's a contrast between the current known industry norms and where we need to move to have confidence in our systems, particularly complex systems, and systems at scale, which tend to be complex systems. So I'm going to illustrate part of the problem by going over some of the myths of availability, because the myths of availability contribute to, again, our confidence in these complex systems. So I'm going to list them real quick, and then I'm going to go back and focus on just a few of them. So the myths are that you can improve reliability of a system by removing the people who cause accidents, that you can improve the reliability of your system by documenting best practices in runbooks, that you can do it by defending against prior root causes, that you can improve your reliability by enforcing procedures, or avoiding risk, or simplifying your system, or that you can improve reliability by adding redundancy. These are all myths, meaning they're stories we tell ourselves to make ourselves feel better, but they aren't necessarily true. And I'm going to focus on a few of these that I'm pseudo-randomly picking here, because the truth tends to be counterintuitive. And I'd like to, I don't know, start some drama, stir up some controversy for the Q&A section. So I'll focus on this one, this myth that you can defend against prior root causes and that will improve your reliability. So there's a couple things wrong with this concept. One is that it relies on this notion of defense in depth, which means, if you identify things that brought the system down previously and you build defenses to that, you can just keep adding defenses and that will make your system safer. So it turns out that that's not the case, first and foremost, because incidents tend to be unique, especially catastrophic ones, which means you haven't seen them before, which means building a defense for prior ones doesn't help. Adding defenses also increases the complexity of your system, which gives you less intuition about how it will behave during failure. And then my favorite component of this that we can pick at is that in a complex system, there are no root causes. And I really want to emphasize that there are no root causes to incidents in complex systems. So if you have a complex system, and most of us in software at this point do, then if you are doing RCA, root cause analysis, at best, you are wasting your time. And if that upsets anybody, I would happily take that discussion into Q&A or throughout the rest of the day and explore why root causes are a fallacy of complex systems and incidents. So moving right along, another one that we hear a lot in the industry right now is avoiding risk. And in particular, we hear this with the terminology of guardrails recently, the past 3 or 4 years. We've heard that a lot. Let's put guardrails on the processes around deploying and maintaining and operating and troubleshooting our complex systems. That will make it safer, and then we will have a more reliable system. And for better or worse, it turns out that the key component for a resilient system is the adaptive capacity of humans. Humans being able to, as Adrian said, have an intuition about what's going wrong, mentally model new solutions to move forward. And in order to have a good intuition, humans have to be exposed to risk. So by avoiding risk, you do two things. One, you deprive humans of the experience necessary to develop intuition. And you tend to put tools that are obstacles during incident remediation in place. My favorite example of this is disabling SSH. If you have an immutable infrastructure deployment setup, of course it makes sense to disable SSH because you shouldn't have people logging into machines in immutable infrastructure, right? That's avoiding a well-known risk. But then when you do have an incident, your most experienced engineers, what's the first thing they're going to want to do? They're going to want to SSH into the box and see what's going on. Jump down to, then this will be the last myth that I explore a little bit here. This is one of my favorites. If you simplify your system, then it will be more reliable, right? Like the problem is complex systems, so let's just take the complexity out. Turns out that not only is this not a good approach to making your system more reliable, but it's impossible to do without also limiting the potential for success for your system. The potential for success for your system correlates to your ceiling for success, correlates with the complexity you add into it. Makes complete sense if you think of it that way. As a software engineer, you're hired to add complexity to your system. If you, and we can go through some trivial examples to prove that this is the case, but the safest systems are the most complex ones. Or to put it another way, if you have a very simple system, you can only make it safer by adding complexity. You can't simplify a simple system and make it safer at the same time. So as your software project goes through time, as it ages, in order to increase its reliability or add to its robustness, you are going to have to add complexity. So I hope some of those paint the picture of why oftentimes our intuition around our systems leads us astray when we're thinking about things like availability and security and creating more reliable systems. So how do we address this? How do we make it better? Crystal mentioned earlier the dynamic safety, Rasmussen's dynamic safety model. The way that I like to think about this is imagine that as an engineer, you're in the middle of these three poles and you have like an elastic band attaching you to these three poles. So if you walk too far from any of the three poles, the elastic band breaks and for you it's game over. So the three poles are economics, workload, and safety. And this is easy enough to illustrate. As an engineer, I'm sure on your first day at any new job, nobody has a rule that you're not allowed to deploy 100,000 new instances of EC2 or something like that, right? Nobody has that rule, but you know you shouldn't do it because you know stuff costs money. Right? So you have an intuition for how far you can drift from that economic boundary. As a software engineer, you know that your resources cost money, that you cost money, that your team costs money, and you know that if you run out of money, then your business will no longer operate and it's game over. So subconsciously or unconsciously, you optimize for the economics of your solutions, the compromises that you make as a software engineer. The same is true for workload. You know that your machines can handle a certain amount of workload and that you as people can handle a certain amount of workload and you can only get so much done in a day. And if you push those boundaries too far, that band will snap and it will be game over. The same is true of safety. The difference between economics, workload, and safety is that with safety, you chances are do not have an intuition for, I'll just say, you don't have an intuition for how far you are from that pole. And the reason I'm comfortable saying that you don't have that intuition is because we all still have incidents. And the reason we have incidents is precisely because of that reason. We don't know that an incident is about to happen. If we had an intuition for how far we were straying from that pole, if we felt that that band was about to snap, as engineers, we would stop what we're doing and we would fix it so that it didn't happen, right? Incidents, major cascading failures and security incidents, they're surprises. So to the extent that we can build an intuition for that safety margin, we are able to improve the reliability of a system. And that's the foundation, the fundamental theoretical basis behind the principles of chaos, which we wrote up at principlesofchaos.org when we defined chaos engineering. This is my favorite definition, by the way. Chaos engineering is the facilitation of experiments to uncover systemic weaknesses. So we do that by experimenting on a system to gain knowledge, generate new facts, gain knowledge, and build up that intuition of the safety margin that you have with your complex system. So that's one model that we can put out there as a way to combat that and proactively improve the reliability of your system. I'll quickly go through another one just because it's one of my favorites. It's called the economic pillars of complexity. I stole this from Kent Beck. And in this model, you have four properties: states, relationships, environment, and reversibility. And the quintessential example of this model, it's an economics model, is Ford in the 19 teens. So for Ford, they were able to they were able to navigate complexity by controlling that first property, states, by saying you can have whatever kind of car you want as long as it's a black Model T, right? So that drastically reduced the number of states that they had. It controlled that, so it allowed them to navigate complexity better. They were also able to control the relationships in their manufacturing process. They moved to assembly line and scientific management of how they built cars. Their competitors at the time were building entire cars from the ground up with a team. Whereas Ford said, we'll have an assembly line. You'll only be able to talk to the person to your left, not the person to your right. So by limiting the relationship between the parts and the people and the process, they were able to better navigate their complexity. They were able to impact their environment by first breaking up the American Motor Trust and then basically becoming a monopoly themselves. So they were able to enact legislation, for example, to tear up trains and pave roads to enable their technology on the public's dime. And that brings us to the last one, reversibility. Well, there's not really a way that they could undo building a car. So they actually didn't have a lot that they could do in terms of reversibility. So really, it was those first three pillars that allowed Ford to exceptionally navigate complexity. So how does that compare to software? Well, chances are, as an engineer, your job is in part to increase the number of states of your software, not just the data, but also the functionality that your system can perform. Relationships between different parts, anything in comp sci can be solved with an additional layer of abstraction. So generally, we can't affect that either. The relationships, microservices, event-driven architecture, all of that, the relationships between parts is increasing. We can't really affect the environment too much unless we're a monopoly, Amazon, and most of us aren't. So we can't really do anything there, which brings us to a reversibility. And here's where software shines, not just because it's software, not hardware. It's malleable by design, but we also specifically have processes and tools that allow us to reverse our design decisions. This really started in a noticeable way about 20 years ago with the introduction of XP and Agile, replacing waterfall, where, in waterfall, you would make a design, you would build it, you would give it to the customer after a year, and they would say, oh, that's not what I wanted. And you'd say, well, tough, I spent a year on it. Let's just move forward, right? And so XP and Agile came along and said, okay, we'll work for a week, put it in front of the customer. They tell us that sucks, we don't want it. It's easy enough to throw that week away. Reverse that design decision, go back the next week. Oh, that's closer. And hopefully by the third week, you're actually tracking with what the customer actually wants. That's a process way to do it. We also have tooling ways to improve reversibility, source code control, versioning, feature flags, automated canaries, chaos engineering when used in a proper way, and continuous verification is part of that feedback. So we can actually explicitly make design decisions about the tools and architecture that we deploy that improve the reversibility of our decisions, which gives us a lot more power to proactively improve the reliability of our systems. Sorry for the block of text here, but I just love this quote. So I'll quickly read it. The chief merit of software engineering is its technical efficiency with a premium placed on precision, speed, expert control, continuity, discretion, and optimal returns on input. Again, this is just one of my favorite definitions of engineering. Unfortunately, I accidentally regex this. So the actual quote is, that's the chief merit of bureaucracy. But this does come from sociologists, and in particular ethnographers of engineering. So why would they say this? This is ascribed to engineers. Why would they say this about engineering? Bureaucracy kind of has a negative connotation. Why would they say that we're a bunch of bureaucrats? That sounds mean. Are sociologists mean? No, actually, in this case, they're kind of correct. The reason that they call software engineering the bureaucratic profession is because no other industry does a better job of separating the people who decide what needs to be done from the people who decide how it's going to be done from the people doing the actual work. Okay, so that's the ideal model for bureaucracy. And in software, we have people managers, product managers, project managers, architects, chief architects, tech leads. All of those positions exist to take responsibility away from the people doing the actual work to decide what work to do and how to do it, which is the ideal of bureaucracy. And bureaucracy grew up out of a need to formalize engineering, in particular scientific management and Taylorism, so that people didn't mess up the production of like widgets. And in the case of scientific management, cars, which were pre-designed with precision. Now, if you believe that as a software engineer, you're a knowledge worker, then this model does not apply to you at all. Which means that most of software engineering has been doing it wrong since 1913, since Taylorism and scientific management really started to take off. So fundamental basis for why some of these things don't feel right and don't fit right. And continuous verification can help put the attention back, and chaos engineering in particular, back toward the people who are doing the actual work, having the intuition about or more context about what they're doing, so that they can make more of those decisions about how to do it and eventually what to work on in the first place. So I'll leave you with this message: don't fight complexity, navigate it,